So I'd like to start by thanking the organizers for inviting me and for running such a smooth and enjoyable conference. So this talk has two parts. I'll do the discussion of the relation between two-zero theory and five-dimensional super Yang-Mills. There's a second part on the six-loop calculation I did with Byrne-Dixon et al., but I won't have time for it here, but it will be on the web. So we have this two-zero theory, which was reviewed by John Schwartz on Monday for, I guess, almost 18 years now. And in some ways, it's a comfortable part of our landscape. We have various definitions, and we know a fair amount about it. And we have a lot of applications, both physical and mathematical, at this point. But it's still mysterious. It's very unsatisfactory from this other point of view of what would be, even to physics standards, a definition that you could compute general observables from or understand qualitatively why it works. And various things have been tried. The original string theory origin suggested that it could perhaps be defined in terms of tensionless strings. There's a old proposal from those days called matrix theory, which does give you a concrete definition, but a hard one to work with. Finally, one can compactify and try to learn about the theory from its compactified versions. Of course, that's the way that we'll eventually go in this talk. And again, I want to basically point out some of these most basic questions about the theory, which I think are still mysterious, and try to learn about them from that last point of view. Okay, so what do we think we know about it? What we'd be very surprised if evidence came up against these points. Well, it does seem to be a local field theory with a non-fluctuating metric. It has no dimensionless parameters, no relevant operators to go to induce mass scales. You turn on VEVs for the scalars that I described. You go on the so-called Coulomb branch. It has order n cubed degrees of freedom by various measures. There's very recently an interesting, but I argument deriving this n cubed. I understand the theoretic argument deriving this n cubed. Next talk will have interesting things to say about the n cubed. And finally, one point which I wasn't convinced about when I started, but I'm more and more convinced about, which is that not only does the theory have extended objects, such as the strings in the broken phase, tensionless strings perhaps in the symmetric phase, but that they're really essential to the theory. And if you somehow tried to take them out, you would be left with the abelian non-interacting theory. So you have to understand the extended objects. And as I think about them, I realize that they're very strange extended objects because we're used to strings and branes and all sorts of extended objects, but they always have some sort of a fixed scale, or at least a scale that governs their dynamics, and they're classical on scales large compared to that. But clearly, an extended object in a conformal field theory cannot have any preferred scale. Okay, and this is one reason why they're strange and mysterious. And the basic reason I think that these are crucial is coming to the first point that we shouldn't forget. We all know this is this very surprising thing about the theory, that it's an interacting quantum field theory in more than 4 dimensions. And for a long time, the universal wisdom is that there could be no interacting quantum field theory in more than 4 dimensions. And there were a lot of arguments. Of course, there's power counting and normalizability, but there's this even simpler sort of intuitive argument that just looks at the behavior of quantum particles moving in space-time. And it's a good exercise, if you haven't done it, to check that a typical path, either in quantum mechanics or in Brownian motion, the statistical analog, has a fractal dimension too. So this is why a pair of particles can naturally intersect in quantum field theory in more than 2 dimensions, but that goes up to 4. Two-dimensional sheets will naturally intersect in up to 4 dimensions and not above that. And so it's very unnatural to think you're going to get an interacting theory in more than 4. And when you cut the theory off, of course, you spread, the particles get fuzzed out, and you can get an interaction. But as you now try to either take the continuum limit or go to the IR, you lose that. And that's why these interactions in higher dimensions are non-normalizable or irrelevant. They go to the 0 in the IR. And this is, again, in this case where we know what the argument means, weakly coupled particles, this is even rigorous, and they're obviously very restrictive assumptions, but it's a simple and solid argument in those cases. So now the thing which one sometimes thinks, and I had thought that, well, what does that have to do with this theory? It's a strong or order 1 coupling theory because of its self-duality. But what I think I would say, and it's just words, is that, well, suppose there is some loophole to that statement, then it's because we have infinitely many particles that in some way conspire to produce a larger than 2-dimensional sheet in this language of the argument. And that really is an extended object right there. There has to be some way of understanding that structure. And so understanding how you get these extended objects, whether implicit or explicit, is key. Okay, so then what are they? And again, there was this tensionless string idea, and people have made some efforts to make sense of that. You can write a very pretty simple action for tensionless strings. This is Lindstrom, Sundberg, Theodoridis. So this makes the symmetries manifest. It embeds, realizes space-time as the light cone of RD comma 2 modulo scale invariant. So you make conformal symmetry explicit. And these authors show that this string only makes sense in 2 dimensions, where it's not really a string at all. And there's a lot of other inconclusive work in this field, but there are, the intuition of people that worked on it, I'll quote John Schwartz, is that tensionless strings don't make sense for a variety of good physical reasons. And I think we'd all agree that's too strong. What doesn't make sense, there is no real. It's very hard to make no-go theorems, but it's a challenge, and we certainly don't have a tensionless string. Even if we did, well, it has to be very different in another way. It has to be a string that allows defining local correlation functions. So what do we say about it? Well, there's a lot of relevant ideas out there. I think it's a good problem. It could well be that the theory is not local in locality is not manifest. Perhaps it's simpler in twistor space, and that would evade the argument we described. Okay, well, there's the idea that we can't make any of these arguments, and that one, again, the talk would end right here if I accepted that argument. And I think even granting that it's truly a quantum theory and that defining, either writing an action, defining a string or extended object might be only a first step that only allows you to understand the theory qualitatively at best. Nevertheless, it's a first step, and one can then try to use it in various ways. One can use it to define the degrees of freedom to quantize and write a Hamiltonian and the like. So, again, one needs the ideas to think about it. And I don't think we've quite come up with the right idea, so we should look at these concrete things. Okay, so now my main topic is this relation to 5-dimensional Yang-Mills, which we get by compactifying on S1. And on some level, that's straightforward. The self-dual tensor has the same number of degrees of freedom as the vector boson in 5 dimensions. The standard power counting tells us that coupling squared is dimensions of length. And we'll see that this is the radius of the S1 from a BPS argument. The prefactor of the action now is 1 over R is not standard Kaluza-Klein. So it's really not the case that there's some naive simple action in 6 dimensions that reduces to this. 5-dimensional Yang-Mills is non-normalizable, but that doesn't mean that you can't do any calculations. What it means is that, perturbative calculations, what it means is that the effective coupling is the non-normalizable, the irrelevant coupling of dimensions length times the energy scale in the process. And so low energy things in principle you can understand. Eventually, perturbation theory will break down. Of course, if you're trying to understand the UV behavior, then it breaks down. Okay, so now we have BPS objects. So John Schwartz reviewed all this for those who were here on Monday. And I think the key object is this so-called instantonic particle, what we get by looking at the self-dual solutions that naturally, span 4 dimensions and now could depend on time and lead to things that look like particles. And their topological charge instanton number now gets related to Kaluza-Klein momentum in this 6-dimensional interpretation. Again, one can check that. One can check this identification with R5 that way. And then strings in this theory in the broken phase are there, and they're not fundamental objects. They come out as the analogs of monopoles. You can get the various BPS strings of the broken phase that way. So, okay, so these self-dual solutions that we identify with Kaluza-Klein excitations have a lot of, I would say this is conceptually one of the key problems with understanding the theory. Okay, so the one instanton solution has a moduli space, it has a center, it has some gauge orientation, and then it has a scale. The Yang-Mills equation in 4 dimensions with scale invariant, and there's a modulus, a solution of any given size. And so as a classical object, well, indeed, it had no preferred scale, as we expect for the extended object in a conformal theory. But what does it mean? Well, an actual quantum particle will, of course, have a wave function, functional of these things. And the wave function dependence on rho, well, if there's any preferred thing, it can't have any preferred scale. And indeed, anything that looks like a BPS object, in fact, is non-normalizable in both the standard 4 spatial directions and in this rho. Okay, so you can't apply the standard reasoning about collective coordinates in BPS. And you can go some distance in resolving these problems and working in the Coulomb branch and learn quite a bit that way. But it doesn't really answer the question in the unbroken phase. And so I would come back to my comments at the beginning and say, well, yes, the theory has to have extended objects to be an interacting theory in more than 4 dimensions. And, well, in 5-dimensional Yang-Mills, these are the key extended objects, these instantonic particles. They're really not particles, they're really extended objects. Okay, so now let's look a little bit at the perturbation theory. And again, there's standard perturbative arguments that one can make. The non-normalizability of D equals 5 in principle is fixed by embedding it in 2-0 theory. That's its UV completion. And then we can compare that with other, the many, many examples of UV completions. And, I would argue this one, again, is not totally different, but it's somewhat different. So the most well-known examples where you have a irrelevant coupling and a cutoff, you can combine them to get a dimensionless parameter. So the gauge theory of weak interactions, string theory, and so forth. And so that's not the case here. We have no dimensionless parameter in the 2-0 theory. Okay, well, that's not universal. So, M theory in 11 dimensions, we have a cutoff, which is basically tied in some way we, again, don't understand in detail to the Planck scale, the gravitational coupling. And this theory must work the same way. The effective cutoff provided by 2-0 theory is at this same energy scale, 1/R5, as the coupling. But unlike M theory, in M theory, that was again, a scale given, that you set when you define the theory. Here, the 2-0 theory actually doesn't have that scale. It only arises after you compactify. So it's really, I think, kind of unique. Okay, and then one can make this type of consideration more precise. You can worry about all these words. Do they have any definitions? And so you say what you mean by the cutoff in terms of crossover behavior in the 2-0 theory. So it must be coming from something. And, well, what are the alternatives? Well, when I started working on this, one alternative was that, well, maybe the theory is UV finite. That's, maybe we don't actually need a cutoff. Well, we've checked, and indeed there's a 6-loop divergence. Okay, well, there could be new degrees of freedom, which is the usual story in an effective low-energy theory, and that wouldn't be surprising. Okay, there could be that somehow the failure of perturbation theory is crucial, and somehow we either resum or we calculate in some other way when we find that there's no divergences. Or again, it might be that words were misleading and we're comparing things that don't make sense. And the fact that the 2-0 theory is conformal, we might wonder whether the S matrix makes sense. But I think that's a red herring. Although again, there's a lot of subtleties in defining the S matrix, and it's not very clear in the symmetric phase. But again, you can go out on the Coulomb branch, you can break the symmetry a little bit, and then there will be an S matrix, and that doesn't change the UV behavior. So I think that's a red herring. Okay, so I excluded 1 and 4. 3 is too hard to work on, so we're back to 2. So what are the new degrees of freedom? Well, they might be BPS states that we see in the theory. Now, in many known theories, the fundamental degrees of freedom are not BPS, like most of the string theories, but they're finite analogs of, an infinite string. An infinite string can be BPS. Well, you make a little loop of the string. It's not literally BPS, but it's there, and it's fundamental. Or maybe they're non-BPS, although that case is, too hard to think about. Okay, but whatever they are, they only come in. We know what d equals 5. We think we know what d equals 5 Yang-Mills theory is at long distances, and the new degrees of freedom come in at the scalar 5. And so now this is making the point that although there are these strings in d equals 5, they are what would have been the monopoles in d equals 4. You might wonder, again, if strings maybe are the most fundamental degrees of freedom, you can look and see that they're not going to be the things that resolve these UV divergences in this case, is you take the symmetric limit, basically because they don't come in at this scale R5. Their scales are controlled by the symmetry breaking scales. And so that leaves us with the instantonic particle as the candidate state. And that's not to say that, again, that there could be some other formulation in terms of tension with strings, just if you're trying to understand the relation between d equals 5 Yang-Mills and 2-0 theory, the strings don't seem to be the central objects and the ones that fix the UV divergences. Okay, so could it be that these instantonic particles, if we could somehow treat them on the same footing as the perturbative excitations, they would change the UV behavior, and perhaps even we could do calculations and see UV divergences cancel. Okay, well, the general structure of supersymmetric constraints on MSYM is dimension independent. So as is familiar, the quadratic action is not normalized. There's a trace f to the 4 term, which is generated in one loop. Then the next term after that at dimension 10 is generated at all orders, and past 2, 2 and past. And so now using standard power counting, you predict this 6-loop log divergence, contributing, with this, as the coefficient in the effective action of this term. And well, indeed, it diverges as one expects, given the standard perturbative calculation with the standard degrees of freedom. Okay, so suppose we could calculate something. What would we, say about it or expect? And there's a kind of important point I want to make here. So you can think more easily for a variety of reasons by going down another dimension to 4 dimensions, so 2-0 on the torus. And then you could imagine checking, for example, S-duality of the corrections of this full effective action in that case. So that's an interesting constraint. And the interesting point, which is one reason why I think there's something to learn following this direction, is that there's a very simple standard, 0th order treatment of Kaluza-Klein reduction, which is you throw away all the Kaluza-Klein states because their mass goes to infinity as you take the size of the extra dimensions L to 0. Okay, so that's the usual story, but in a theory with UV divergences, in a theory, non-normalizable theory, the UV divergences can spoil that argument, and basically one is integrating out states at a range of energies, and because the non-cutoff theory has a UV divergence, let's be more specific. So we start with 4-dimensional MSYM, which is finite. So up till the energy of these 5 to 4 Kaluza-Klein states, 1 over R4 theory is finite. Now we've passed R4 and the theory is effectively 5-dimensional and we have divergences, but then eventually they get cut off by this mysterious 6-dimensional physics. So the point is that there's this range of energies which is giving quantum corrections, and it's their ratio that appears in the quantum corrections. So we saw that this controls the lower limit, this is the cutoff. So as you take the size of the T2, as you take both of these things to zero at the same rate, that ratio stays fixed. And so these quantum corrections remain even in this, Kaluza-Klein, this limit where naively you could just throw away the massive states. Okay, and so, again, it's something which has a lot to do with the scale invariance of this theory that one has to worry about at this point. And these kinds of corrections would survive in the effective action and might be problematic. And the simplest way to get rid of them would be, well, if there were no such divergences, but it can happen in other ways, okay? It could be that they turn out to be suppressed as powers of L. And again, there's a somewhat detailed discussion of the subtleties in this type of argument that in my paper about this. But a case where you can be quite clear is this trace after the 4 contribution, which is finite and is only one loop. And so the one loop answer is easily computable. This is the coefficient of trace after the 4, and it's also clearly wrong because it's not S-dual. And so there's a simple ansatz you can make. Let's add in the particles that would be the Kaluza-Klein particles of the 6th dimension. And so that's a simple S-dual extension of the amplitude. It hasn't been checked so far as I know, but it's a very plausible extension. And it gives the example of how one might try to treat these extra states. Okay, so this is what the 6th loop correction looks like. It looks like log tau because it's a log divergence, and we've fed in the ratio of the 2 scales in the way that was described on the previous slide. And this sort of thing, again, is really quite problematic. It's either, I think, as one thinks about it, it goes away in some way, or it means that you can't use perturbation theory at all to understand UV behavior, which either alternative is possible. But the simple way to proceed, again, is to say that, well, let's try perturbation theory. It might work. And we have candidate states that could change the UV, and they clearly can change the UV behavior. We might see it in perturbation theory. And since we've already seen all the BPS states in this 5-dimensional description, there's no need to think that we need to add extra states to the theory to make sense of it. We just need to figure out how to use the states that we have. Okay, so I don't have a lot of time, nor a great deal of success at this point in doing this. In a way, the most direct way to do it would be to either laticize the 5-dimensional theory or to define it using what's called deconstruction. And that is useful as an exercise to convince oneself that the theory makes sense, but it's not so useful as a calculational tool. If you look through the details of deconstruction, this is this idea that you make a chain, a ring of 4-dimensional theories. So you've discretized one of the dimensions. You check that the actual bare coupling of each of these 4-dimensional theories has to go to infinity in the continuum limit. So it's very hard to do direct calculations feeding in 4-dimensional information, but you can still regard it as a definition of the theory. Okay, and then you can ask questions, well, could these instantonic particles contribute to perturbative amplitudes at all? And whereas solitons generally have form factors that are exponentially small, recently Papageorgakis and Royston have actually shown that that's not the case in this theory, basically because there's this scale size modulus, and integrating the scale size modulus down to 0 removes that exponential. Okay, so they can contribute at all scales, and one can imagine either developing an ansatz like the one-loop ansatz I described by calculating or guessing the couplings. There's been work on that. There's been work on trying to write actions to describe these extra states. It's fairly preliminary, but the difference with the old project of writing a 6-dimensional action basically is that these actions could be non-local, and indeed they are non-local in the 6th dimension because we're using them as shorthand to describe states that came as extended objects in 5 dimensions. So I think it will be interesting to see if one can use this in some way. So I'll just repeat in closing this comment that I think understanding which is the appropriate extended object, and again in this 5-dimensional case, I think it is these instantonic particles, I think is the key to making progress and understanding the mysteries of these theories. And let me stop there.
Thank you. Question or comment? Yeah, Mookie.
There is a duality under which these strings stretched between parallel 5 branes map onto D3 branes wrapped on a vanishing 2 cycle. So in type 2b. So I mean, that gives a setting where the tensionless string is at least defined, well defined in terms of some known object. Is that not?
Well, it doesn't sound any better than a membrane shrinking to 0 size. If you're wrapping a brane on a shrinking cycle, why is the D3 on the 2 cycle better?
Because
than
the membrane has no coupling constant, so it's a strongly coupled system. So this is a string in the membrane, but on the other side, it's all in string theory, and I suppose everything can be weakly coupled.
Well, it might be worth developing, but I think those objects are as strongly coupled as the others. Yeah.
Okay, any other question? So if not, thank the speaker again.